Hello, everyone. Welcome back, or welcome for the first time. I think some of you may have tried to join yesterday at this time, and we're thankful that you tried to join. We didn't realize we'd have so many people join, and we hit our 100 limit before the thing even started. So we're very pleased that you were able to readjust your schedules and show up today. We have 500 person limit now, so I think that should be no problem. So thank you very much. My name is Eric Siegel. I'm helping organize the webinar series, and we have on the call with us Mark Halverson, who will be giving the session. So just a quick couple notes. We are recording this, so if you ask questions, make sure they're good questions. But also we'll be put this recording on the website. So if you missed something and you want to see it again, you'll be able to review it. If you think something's interesting and you want to pass it to a colleague, then you'll be able to pass that link. And these will go on the RBR website under webinars. There'll be a button that says view recording after we post it up there, which should be later today. Mark's going to give his presentation. It's about 20 minutes or so. And for questions, I want you to do two things. One, you can text the question into the chat group, and a couple of us will try to provide some real-time answers to it. But we're going to let Mark continue with his presentation and not try to go back and forth answering texts and answering questions. Or you can keep the question in your head, and once we're done, we'll be sticking around, and we'll have plenty of time to answer all of your questions verbally. So you can either text the question in the chat group and we'll answer it, or you can wait until the very end. I think that's it. So Mark, please take it away.
Yeah, thanks, Eric. Yeah, again, my name was Mark Halverson. I'm a oceanographer here at RBR. I'm a PhD grad of UBC and of Rich Pavlovich, if you happen to know the name, if you're an avid MATLAB user. Yeah, today I wanted to talk about the inductive conductivity cell. So this is the technology that RBR uses to measure conductivity. There are multiple ways to do it, but only two are commonly used in the ocean. So either electrode-based or inductive cells. RBR uses the inductive conductivity cell. I want to point out that essentially all the information here is available in a white paper or that we wrote for a trade magazine called Sea Technology. And so this is a short 4-page basic paper on the inductive technology and some of the advantages and disadvantages of this particular conductivity cell. And so the links are shown on this particular page. Okay, so you can find the publication there. It was in the February 2020 issue. So here's a photograph of our CTD on the sensor side of our CTD. This one looks like it was freshly out of the ocean. The things I want to point out here is that you should be able to see. I'm going to try to draw on the screen. So, excuse me. Here we go. Back to the slide. Yeah. So just a few things to point out here. The thermistor. I'm sorry. I'm having a time enabling my pen. Let's try this again. There we go. Okay. So here's the thermistor. Okay. This is a long. Sometimes it's called a sting. Here, and then the actual thermistor bead is is embedded in the inside the end of the thermistor sting. This is the conductivity cell itself. I'll go into much more detail about that, of course, in a second. And the pressure sensor on our CTDs is typically located on the sensor end cap behind this little small protective window. Okay. I'm pointing out here too that it's I actually in about a month or so I'll be giving another talk that's about the dynamic performance of our CTDs, and I'll get more into about why it's really important that the thermistor here is sort of co-located with the conductivity cell. It's an important feature of our CTDs. Point out too that we make CTDs for different depth ratings. The one I just showed was a 750 dbar cell. They look quite similar. The basic design is the same, but you'll see as we go to higher and higher pressure ratings, there's a more substantial amount of material just to withstand those high pressures. this would be, for example, most sort of loggers, CTDs for coastal applications would be this particular cell, the 750D bar. So, this would be a sort of our deeper CTD. This is commonly what's found on Argo floats, or most profiling floats. This is the 2000 decibar cell. And this would be our much deeper cell for sort of open ocean applications. Okay, so let's get into how these things work a little bit. So into the measurement principles, so the basic principle here is we're going to induce a current in the seawater, okay, and that's done by the sort of basic physics behind this is Faraday's law. And so Faraday's law goes back, one way to summarize it is it's the, if you have a variable magnetic flux will drive a current in the circuit. And if you think back to sort of your early physics courses, that's, if you take a bar magnet and pass it through a loop of wire, you'll actually induce a current if the bar magnet is moving. So that's really at heart the basic physics of how these cells work. And another way to describe it is that it's basically a transformer that's would be used in say AC circuits to step down or isolate components in an AC circuit or to change voltages. So in fact, there's different ways to use inductive cells, or sort of different designs or different topologies, I guess, for inductive cells. And in particular, RBR uses what's known as a double transformer design. Okay, and I'll get into this on the next slide a bit, but what that means is there's two independent toroidal coils of wire within the conductivity, within this housing here, within the cell itself. This, in fact, is not a particularly new idea. Picard, I think this was Auguste Picard, the Picard family, a family of scientists and inventors, including one of the Picards who invented one of the first bathyspheres. Anyways, introduced this, the idea for using the sort of double transformer to measure the conductivity in electrolytes 100 years ago. And it was more or less independently reinvented by fellow M.J. Relis at Woods Hole, actually, at MIT in 1947. This is actually a master's thesis here. And in fact, if you're interested in these publications, I gave links below. Now you might wonder, if it's 100 years old, why do we still use it? Well, it turns out the devil's in the details. So the electronics behind this are rather sophisticated, and it actually takes a lot of tricks electronically to produce a very high accurate measurement. And RBR has invested a lot of time in doing that. Now, to go on a little bit more about how these things work again. So inside the cell, there's two coils. So this would be a ferrite coil, a ferrite ring, and there would be, you can imagine a wire loop coiled around here. Okay. So there's two of them. There's a so-called drive coil and a receive or pickup coil. Okay, so we got 1 and 2 here. So what we're going to do is we're going to apply an AC current to a drive coil. Let's just call it this one. It doesn't matter which. Okay, and that's going to generate a magnetic flux in the ferrite itself. So in this circular ferrite, that induces, in fact, an electric current in the seawater, and or an electric field, and that field drives a current. And that current, that field as it passes through, or the current, excuse me, as it passes through the other coil, induces a signal inside this coil, which is then picked up. Inside this ferrite, which is picked up by this coil, which is then measured. But the upshot of this is that we induce a current with one, and we measure it with the other. Okay, but the strength of the response of that's measured by the pickup coil is proportional to the conductivity of the seawater. Actually, the conductance, but we then apply a cell constant to get a conductivity from it. So that's really the basic thing here, and it's fundamentally a linear system too, which is very important for calibration reasons. Why a couple of pros and cons about this this technology. One is that these cells can be built with a low aspect ratio, which means that the cylinder can be relatively sort of squat. In other words, the bore through the center of the cell can be large compared to the length. And what this means is that the cell can flush naturally just by the motion of the instrument through the water. Right, so that then means we don't need to pump it. Oops, my fault. That means that without a pump, we don't need to. The power consumption is quite low. It also means the cell is sort of acoustically quiet, and so this is important in particular if you're using on glider applications with passive acoustics or turbulence measurements. Okay, there's no pump creating any noise or vibrations. It's a robust design. It's and it's also contactless, which is important because with electrodes can actually corrode to some degree, and we're less affected by surface oils. There are workarounds for these sort of things, but we don't even have to deal with that at all, because there are no electrodes here in contact with seawater. I think probably the main downside, and the thing that we're going to discuss in the next little bit, is that the measurement of conductivity is most, let's put it this way, the signal that the instrument measures, conductivity cell measures, is highly sensitive to what's happening inside the cell. Okay, so in a sense, most or the bulk of the measurement is happening inside here, but the cell can pick up changes in conductivity out here. Okay, which means that anything in the field of the cell can distort the measurement. Okay, and that would be one of the things that we need to address here. I'm going to call it con, but there are ways to get around this. Okay, this is not a limitation in many cases. Okay, so we're just calling that proximity effects. So let's get into that a little bit. So the first thing I want to point out here is that, just to summarize again, any material within close proximity to the cell will change the measured conductivity. And so we always recommend that that the surrounding 15 centimeters of the cell, that's actually too big of a circle anyways, but should be kept free of objects. That unless the CTD is calibrated with that object nearby. So in this case here we have a guard around the conductivity cell, but that's okay because we can calibrate it with the guard in place, and then we don't have to worry about those near field effects anymore from that particular guard. Now, if you do happen to introduce something into the field which was not there when the instrument was calibrated, you will find a bias. If in fact, you introduce a piece of sort of bare mooring wire or a stainless protective cage, they're going to bias the conductivity high, and that's just because metal, steel for the most part is more conductive than seawater. If you have a insulated mooring line or any other kind of non-conductive material or poorly conductive material, piece of rope, or you may bias the measurement low, okay, because those measurements are those materials are poor conductors relative to seawater. And as I mentioned before, this is only a problem if you haven't calibrated the instrument with these objects nearby. So in the case of a CTD guard, we just can calibrate with the guard in place on an Argo float. We actually take the end cap from the float and then calibrate the CTD on it with any kind of antenna or DO sensors or anything else nearby. And so then we don't need to worry about near field effects in that case on Argo floats. And also the final thing to point out too is that not only do objects influence the measurement, but the air-sea interface will. Okay, and so you can measure conductivity very accurately until the cell is just 10 centimeters from the air-sea interface. You know, so that imagine this instrument was, yeah. So okay, so moving on, that's a bit about proximity. A couple, if to attach some numbers to it, here are two different cases where we had a insulated steel mooring line with attached, um, and then to it was attached our CTD with different clamps. So here's a 75 millimeter clamp and a 100 millimeter clamp. And so in seawater, the error in salinity that resulted from having this insulated mooring line nearby was almost essentially undetectable. I mean, much less than our calibration error. I mean, this is a tiny, tiny number. Now with the 75 millimeter clamp, of course, then the cell is closer to the wire. And in that case, we found an error that's basically at about what you would call the calibration specification. So 0.0025 in salinity, which is about what, it's kind of the equivalent. We don't calibrate in salinity, but that would be roughly the calibration error, you know, salinity error, if you want to put it that way. Or that would be the effect on conductivity is enough to cause an error in salinity of 0.0025. Okay, so these are quite minor. And in fact, if you're doing any kind of work in an estuary where you have a huge salinity signal, these things aren't important. Rocky Geyer mounts our instruments on a rigid mast with the cell quite close to the mast, and he has found, you know, while there might be a small bias, it has actually zero impact on the science because, you know, in an estuary, for example, the signal is so big. And you know, I did my PhD in estuaries and a lot of my postdoc work, and this just is not important in that particular case. Okay, so that's a little bit about the proximity errors that you get. Okay, and part of the reason that this is in fact so small is because, again, the bulk of the measurement is made inside the cell, and so there is only a relatively weak sensitivity to this volume out here. And if you think about the volume occupied by this wire with relative to this whole volume, it's quite small. Okay. All right, I'm going to move on a bit now to the accuracy, resolution, and stability of our conductivity cell. This is from the sort of calibration perspective. This is what we have. We have an accuracy in conductivity of 0.003 millisiemens per centimeter. That's the same as 0.0003 Siemens per meter, if you're used to using Siemens per meter. The precision is about 0.001 millisiemens per centimeter. In fact, if you just put the instrument in still water, the RMS noise level is actually lower than this, but you know, this is what we put on our spec sheets. And we also, the sort of calibration is stable to within 0.01 millisiemens per centimeter per year. Okay. I want to show you a case where we were able to use the RBR inductive cell to measure some very fine structure to highlight the high resolution of the instrument. And so I'm going to do this by showing a profile taken from a lake near Powell River. So Powell River is a small town on the Sunshine Coast of British Columbia, a couple hundred kilometers northwest of Vancouver, in fact, where I'm based. And Powell Lake here, in fact, was a fjord 10,000 years ago. And then it got cut off from the ocean by isostatic rebound as the glaciers retreated. And that means the bottom of it's filled with seawater, but it has a river input, which means the top of it's filled with fresh water. And the seawater has been cut off from the ocean for 10,000 years. Very interesting biogeochemistry happening down there. In fact, if you send it down a Niskin bottle and bring it back up, it fizzes methane gas. It's a crazy place, highly anoxic. But it's also geothermally heated, and so there's some very interesting physics. You have a situation where you have warm, salty water below cold, fresh water. Okay, and so I went out there a couple of years ago with Rich Pavlovich, an opportunistic cruise. I attached, we have $50,000 of instruments attached together by tape and wood, typical thing in oceanography. But then we just profiled this whole package here very carefully through this very interesting thermohairline structure, as I'll show you in the next slide. So as it turns out, again, so the bottom of this lake it's 350 meters deep, but it's heated from below and it's salty. So this is the perfect area to set up the diffusive instability. And what that gives you in the end is this very interesting thermohaline structure. And so you have these uniform steps of about 1 meter thick, okay, like this, separated by very sharp but sort of weak interfaces here, okay? Those are only 10 centimeters thick. The temperature change between these layers is milligrees, and the salinity change is 0.002345 between these layers. And so on the left panel here we have, this is conductivity, and this is temperature. And so you can see in temperature we resolve these steps very well. By the way, this is the reference here was a Seabird 25, or the other instrument here is a Seabird 25 at 4 hertz. We sampled at 12 hertz. And then conductivity is on the left panel here, and you can see that we've done just as well of the job as characterizing these steps. And I find this really interesting because we have a cell that has a sort of an effective sampling radius of, it's sensitive to changes on the scale of 15 centimeters, but it's very easily measuring these interfaces, which are thinner than 10 centimeters. And I think that really reflects the fact that, again, the bulk of the measurement occurs within this conductivity cell itself. And I just point out too, if you're interested in reading more about this lake, there's a paper below that you can reference to read more about this lake. So that's just to highlight the sort of science that can be done, very fine scale, not fine scale turbulent, but very small, weak signals can be picked up by the instrument. A bit about long-term stability of the sensor. Instruments are routinely sent back to RBR for calibration, so we can estimate a drift rate of that. We can just take the data of 2 successive calibrations, calculate an error, and divide by the time between calibration to get a sort of drift rate. So here there's 100 or so instruments, perhaps. And what we're plotting is a histogram of drift rate from these instruments that have been returned to RBR for calibration. The average is quite close to 0. So the dispersion of this curve here is of this distribution is, standard deviation is about 0.004. So that's, 60-something% of the instruments drift by that amount between calibrations, which is just above, in fact, our calibration accuracy. So recall on our spec sheets, we put 0.01 millisiemens per centimeter per year as a very conservative estimate of the stability. So that's the results from our calibration lab. And the other way we can estimate the stability of the sensor is actually using in situ data on Argo floats. So a number of floats have gone out, Argo floats have gone out now with RBR CTDs on them. And we can use that data and compare it against oceanographic, references. We can compare those against references to assess whether or not the salinity or conductivity coming from an RBR CTD is stable. And so this is just one particular float of the 4 that we've been analyzing recently. So this float was deployed by the Argo program in China, in the Western Pacific. And what we have here is this is the salinity from the float relative to the reference database. And so this is actually, and we're using some standardized methods to assess the stability of this float. So the float does not drift at all, and in fact is even calibrated very accurately. So the error here is just around 0. You know, although it appears there might have been some drift happening here, we in fact go back and look at other floats from the same region, and we find that in fact they do the same thing, which is just to say that the reference database is not capturing some of the local variability very well. And so this is another case where we have shown that the instrument drifts in fact, it doesn't drift at all. In fact, it performed a very stable measurement over the period of about 2 years now. So this was in January 2018. It was deployed. Yeah, and so that's it for now with the inductive cell and its performance. Before we get into questions, I wanted to just point out that some of the upcoming webinars that we're going to be doing very quickly here. Next week, Greg will be talking about the BPR quartz, or bottom pressure recorder. A week after that, Eric will be talking about our oxygen optode and its performance, in situ evaluation of its performance. Moving on, we'll hear a little bit from Chris Contos at Del Mar Oceanographic and our partnership with them in assembling wirewalker systems and deploying them. Some Ruskin Mobile from Candace. And then moving on into May, I'll speak again about dynamic performance of the CTDs. And Nikolai from RBR will talk in detail about, in fact, that last slide I showed about the stability of the instruments from Argo floats. Eric will get into the Legato, our glider CTD, and then finally at the end, well, sorry, at the end of May, then Matt from RBR will talk about the Eco CTD, which is a use of our CTD on a rapid profiler, underway profiler. And then finally, early June, Ray from RBR will talk about RSK tools, which is our MATLAB toolbox for visualizing and post-processing RBR data. So with that, I thank everyone for showing up, and we're ready to take questions.
Yes, thank you, Mark. That's a wonderful presentation. And so Mark and Greg and myself and others from RBR are standing by to answer any questions. I think you've seen many of them go through the chat channel. But what we can do now is you can unmute your mic and you can ask a question. We can address it the old-fashioned way.
Well, I guess we can start reading through chat window questions here. We had a question from Greg Oldenburger. I meant to ask about the drive frequency of the EM circuit. Is that something you want to handle, Greg?
Sure, I can do that. One Greg to another. We're in the kind of high audio band, so tens of kilohertz typically is where we run conductivity at. There was also a suggestion that for the benefit of people who are going to look at this presentation afterwards, we could go through the questions that are here, but I think we'll just add those in audio afterwards so that people can get them. I hope I've managed to answer online most of the questions that have been asked. So I think we'll wrap it up at that point. Oh, I just see Rodrigo's question. Mark, do you want to answer that one?
I am.
Very bottom.
Oh yeah. Well, conductivity is yeah. I didn't even mention this at the beginning. Conductivity is one of the things, along with temperature and pressure, or those are the three things you need to compute salinity in the ocean. Yeah. And conductivity is actually, it's probably it's in a way it's the hardest and most mysterious perhaps of those three measurements. So it's and there are different ways to do it. So it's really worth discussing because it's a difficult measurement to make, and that's why we wanted to talk about it. And we have a slightly different approach than in using the inductive cell than other manufacturers.
Great. Well, thank you everybody for coming, and pleasure having you. We will be putting the show out. The recording will go out on YouTube afterwards, and so we'll be able to post the link to that afterwards, and hopefully we'll see you at next week's webinar. Thanks very much.
Thank you, everyone.
Okay. Bye-bye.